Good morning, everyone. My name is Kai Shi. I graduated from NC State and recently joined the Northwestern as a postdoc. What I'm going to talk about today is part of my PhD work at NC State, and it is about the microscopic pressure tensor. And especially in this talk, I would like to focus on one fundamental question about this microscopic pressure. That is, if we can have a unique definition of the microscopic pressure. And our interests on the pressure at nanoscale arises from the so-called high pressure effect recently discovered in confined phases. It basically says some reactions or phase transitions can only occur at the tens of thousand bars in the bulk would readily proceed in the nanopore or near a strongly wetting surface, even when this confined phase is in direct contact with ambient pressure. For example, people found a conducting sulfur chain and high-pressure crystal nanophases in the carbon nanotube under the ambient pressure. And they also found the spontaneous hydrolysis reaction between the two graphene sheets under ambient pressure. And all of them are carried out without catalysis and under very mild conditions. Without help of the confinement, this phase transition and chemical reactions require several gigapascal in the bulk. Especially in the first case, the sulfur in the bulk requires 90 gigapascal to become metallic. Although the mechanism behind the phenomena are not straightforward, and intuitively, the microscopic pressure inside the pore may play an important role here, just like the way the bulk pressure plays in the phase transition and the chemical reaction in the bulk. So looking at the microscopic pressure directly might help us understand what happens inside the pore. So what is the pressure at the nanoscale? As we all know, the pressure in the homogeneous bulk is a scalar, and it has the same value everywhere in the system. But if we look at a system in a nanopore, the system now is called inhomogeneous system. And the pressure in the pore is a second-order tensor. Here, PR is the pressure tensor at a point R in space. And it has three non-zero diagonal elements if the system is not under strain. As in the bulk case, the pressure tensor can also be decomposed into the kinetic contribution and configurational contribution. The kinetic contribution is from the thermal motion, and the configurational contribution is from the intermolecular forces. For example, in a slit-shaped pore, there are two components of the pressure tensor. The one is the normal pressure, which is perpendicular to the surface, and this normal pressure is a constant and well-defined. And the other component is called the tangential pressure, which is parallel to the surface. And the local value of the tangential pressure depends on the distance from the surface. Now, a fundamental difficulty actually comes in, that is, local tangential pressure is not uniquely defined. If we look at the equation for the configurational pressure tensor that is derived from the statistical mechanics, we will notice that the local pressure depends on an arbitrary contour connecting the two interacting molecules. So for the normal pressure component, the final equation is independent of this arbitrary contour, so the normal pressure is well defined. But for the tangential pressure, there's no way to get around this arbitrary contour. So the tangential pressure is not uniquely defined. And there are actually many possible choices for the contour. And here I only showed you two possible choices. And one is the straight line, which is adopted by the Irving and Kirkwood. And the other one is called the Acknowledgment choice, which is composed of two perpendicular paths. And this arbitrary contour involved in the equation actually indicates that there is an ambiguity on how to distribute the force between the two particles in space. And in fact, not only the pressure, but all the thermodynamic functions are not uniquely defined at the nanoscale. A familiar case is the pore volume or pore width. Here I listed three popular definitions of the pore width. You can define the pore width as the distance between the center mass of solid atoms, which we call the physical width, and it can be directly measured by neutron diffraction. And the people in the absorption field would probably prefer the middle definition, which is the internal width. And the internal width is defined as the available space to the whole adsorbate molecule. And the pore volume delimited by this internal width is actually corresponds to the quantity that it can be measured from the gas absorption experiment. And of course, the people also argue that the pore space should exclude the dead space near the wall, which is inaccessible to the center of the molecule. So from this perspective, we can also see that the pressure inside the pore is not unique because the pressure is a conjugate of the volume. And the objective of our research is to understand and try to define a unique microscopic pressure. So far, I have explained why we had difficulties with the microscopic pressure tensor, and especially why the local tangential pressure is not uniquely defined. So the question that we ask ourselves is, can we define a unique effective tangential pressure by spatially averaging the local value over some sensible volume? In this way, we might get a value of pressure that is independent of arbitrary contour, and also we will have a volume that is well defined in space. And here is how we define this effective or coarse-grained tangential pressure. On the left, I showed you a snapshot of the fluid structure near a solid wall, and on the right, we have the corresponding density profile. And x-axis is the z-distance from the wall. And you can see the fluid shows a strongly layering structure near the solid. And what we did is to divide each adsorb layer into a separate bin. For example, the first bin contains the first adsorb layer, and the second bin contains the second adsorb layer, and so on. And the bin width is denoted by the delta z. And then we can calculate the coarse-grained tangential pressure in each bin by spatially averaging the local tangential pressure over the bin volume, as you can see from the equation below. And the questions that immediately follow are whether the defined coarse-grained tangential pressure will lead to a truly unique value, and if so, what value is the appropriate bin width? So to answer the first question, we were actually able to prove that our effective tangential pressure can be truly unique if an appropriate bin width is chosen. But in the interest of time, I'm not going to show you the full derivation, but instead, I'm going to show you the essential idea we took here. Let's look at the first bin width in the density profile, which corresponds to the first adsorb layer near the wall. And now we can take two trial bin widths for the first bin, and the first trial is the delta z prime, and the upper boundary of the first trial is close to the first density peak. And we can also take a second trial, which is the delta z double prime, and the upper boundary is close to the second peak. And we were able to show that the majority of particle pairs have the relative position shown on the left for the first trial bin width. And in this case, the vector im plus the vector im is smaller than the vector ij in the x direction. And for the second trial bin width, interestingly, the majority of particles have the relative position as shown on the right. And in this case, the vector im plus vector im is larger than the vector ij in x direction. And based on the above argument, we can actually show these two inequalities. And these two inequalities clearly indicate that there must be one bin width that will make our coarse-grained tangential pressure unique. And this coarse-grained tangential pressure will be a constant, which is independent of the arbitrary contour. And this proof can also be extended to other bins. So now we need to figure out the appropriate value for the bin width that can make our coarse-grained tangential pressure unique. And to find this answer, we have to resort to the molecular simulation. So here I showed you a local tangential pressure profile on the top and the spatial integral of the local value at the bottom for a carbon slit-shaped pore filled with argon molecules. And the background figure is the simulation snapshots, and we can see only 2 sublayers can be accommodated in this pore. And we calculate the local tangential pressure by 4 different contour definitions. And these 4 different definitions, they are just 4 different ways to assign intermolecular forces to a local point. And mathematically, all of these contour definitions, they are equally valid. As expected, different contour definitions give different local pressure value, which reflects the non-uniqueness of the local tangential pressure. But interestingly, if we integrate the local pressure over some distance, as we showed in the bottom figure, and all different definitions converge to the same value at some point, and those convergence points are marked by letter, the point A, C, E are the convergence points that are predicted by our mathematical proof I just showed you in the previous slides. But we also notice there are 2 additional points, B and D, here, and we can confirm these 2 points are also truly convergent for all contour definitions. And we miss them because of our coarse-graining system. Based on these convergence points, we can calculate the beam width, delta Z1, for the first beam, equivalently for the first layer, as marked by the green arrows in the figure. And the coarse-grained the tangential pressure defining this length scale should be unique for all contour definitions. And based on our coarse-graining system, the coarse-grained tangential pressure we have calculated so far can be viewed as the unique tangential pressure inside each sublayer. But what about the unique tangential pressure inside the entire pore? So here, instead of defining the length scale for each sublayer, we can actually obtain a length scale comparable to the pore width based on the convergence points A and E. And we call it unique pore width. From this integral plot, it is clear that the coarse-grained tangential pressure defined over this unique pore width should be unique. So do you still remember the difficulty of choice for the pore width that we have mentioned at the beginning of this talk? Now, it will be very interesting to compare this unique pore width with other popular definitions of the pore width. On this left figure, we have the full comparison between the different definitions of the pore width. We calculate this unique pore width that give rise to the unique in-pore tangential pressure for 3 different wetting parameters. And the wetting parameters is a measure of the strength of intermolecular interactions between the fluid and the wall. Interestingly, the unique pore width is in good agreement, as you can see here, with the internal pore width. But they are not equivalent. The internal pore width is purely geometric in definition, but the unique pore width should depend on the molecular interactions. For now, what we can say is the internal width is a good approximation to the unique pore width that leads to a consistent thermodynamic description of the confined system. But more investigations are still needed before we can fully understand the physical meaning behind this unique pore width. To conclude, in this work, we have attempted to solve one of the most important fundamental questions about the pressure tensor, that is the uniqueness of its value in an inhomogeneous system. We prove and show that by integrating the local tangential pressure over a small region space, we can obtain an effective or coarse-grained tangential pressure that appears to be unique and free from the ambiguous definition of the local pressure tensor. And once we have uniquely defined the pressure inside a nanopore, the difficulty of finding the boundary of the system immediately goes away. And the unique pore width comes out naturally as the pore width definition in this case. And we found this unique pore width agrees with the internal pore width, the definition of which is widely adopted in absorption field. Although we have showed solid evidence here that the coarse-grained tangential pressure is unique, We will still stay cautious about our results because there are still many things about the pressure tensor that we have not understood. In the future, we plan to find more evidence to support our argument here. One of the important steps among them is to verify this coarse-grained tangential pressure from the experiment. So the local pressure tensor is a highly controversial topic in statistical mechanics. And during my PhD, I actually received many criticism and questions about my research. And sometimes I even doubted myself. So I would like to take this opportunity to thank my PhD advisors and all of my colleagues and collaborators for their support and helpful discussions about this topic. And I believe one day this long-standing issue would eventually be clear, and I hope we are heading to the right direction. Thank you for your attention, and if you have any questions, you can message me or attend live chat. I have my contacts listed in my poster. Thank you very much.